Welcome back to video number 3 in my Calculus 3 series of Intro to Mathematica videos. In this video, we are going to start moving into some actual Cal 3 material. In the previous 2 videos, I kind of did an introduction to Mathematica, how it works. And then in the last video, we touched on some of the basics that come from Calculus 1 and Calculus 2. So in this video, my goal is to cover all the stuff that you will need to know from the idea of parametric equations in 2D. Now, in a later video, you'll hear me refer back to parametric equations again, but in that video, we'll be more in a 3D sense. So let me begin by sharing my screen again, sharing my Mathematica. So remember, we're always working within a blank notebook file. This time I went ahead and opened the palette for us. Oops, I think I just got rid of it. So let me bring it back. There we go. So my palette's already open. That way we can use it if I need to. And so let's get started. So as you're learning during class, or have already learned during class, parametric equations in 2D require you to know 2 equations or 2 functions that we will eventually combine into a non-function problem. So in this case, we typically use x of t and y of t to do that. So let's begin by defining our first parametric equation. I'm going to begin by defining x of t is equal to t squared minus t. I'm going to input that function. And then I'm going to define y of t is equal to t squared plus t plus 1. And so remember, if you need a refresher on how to define functions, I cover that in my first video. So with parametric equations, there's a few things that you have probably seen during lecture that I want to show you how to do in Mathematica that might be of assistance when you go to work on your Mathematica project. So the first one is, how do you graph a parametric equation, or what we call in class a parametric curve? So in Mathematica, there's actually a built-in code for us to do this parametrically. I'm going to begin by starting with a capital P and typing out the word parametric. Now you'll see there are a few different codes that start with parametric. Some of these you will never use, so don't go too deep into them. Really, the 2 that you're going to see me use over this series of videos are these top 2. One says parametric plot 3D, and the other one just says parametric plot. Since we have not gotten into the 3-dimensional stuff, let's just stick with the second one on my list, which is the parametric plot assumed to be in 2 dimensions. So I'm going to click on that. I'm going to click on my double down arrow. And as I read the descriptions, it looks like the first one is the one I'd like to do. It says it generates a parametric plot of a curve with x and y coordinates, fx and fy, as a function of u. So let's click on that one. And what this built-in code is asking you for is it wants you to define what your x and y are. So you could either type these in explicitly as we did up here, or now that I've already defined my functions, I can simply do x of t and y of t. Now you have to also tell Mathematica what is your variable. Obviously, we're not using u's in this problem. We're using t's, and see everything turns green. And just for an interval for us to work with right now, let's go -3 to +3. We can mess with that in a few minutes if it's not right, but that's a good starting interval. So let's graph this curve and see what it looks like. There you go. Now, one thing you will notice is that Mathematica does not put the arrows on there for you. If you really want to see what direction it's going, you could plot it out on paper, but I'm not going to ask you to do any of that on a Mathematica project. I'm more worried, especially in an intro project like this for calculus, is if you can get the curve, I'm happy with what you're doing. So you can do and mess around with this. Parametric plot is the easiest way to graph parametric curves in Mathematica. Now, as far as the application stuff goes, one of the first things that we did during class was we learned how to find the equation of a tangent line to a parametric curve. So what I would like to do is we're going to use this exact same x and y, and we're going to use this curve, and let's find the equation of the tangent line. I believe we're going to do t equals 1 for our value. And then once we find that tangent line, I want to put that tangent line on this graph to see how accurate it is and make sure what we found is what we're looking for. So during lecture, you might remember that in order to find the equation of a tangent line parametrically, you have to first find the derivative function. The reason you find the derivative is because you want to use that to help you find the slope. So actually what I'm going to do in Mathematica is I'm going to define a slope formula. So I'm going to call that m of t because we typically use m as slope. Now, to find the slope of a tangent line, we need the derivative. But in parametric, the derivative is not just one derivative. In parametric, you have to then do a fraction. And in the numerator, you would take the derivative of your y function. So you remember back in the last video, we learned how to do derivatives. We're going to call that y prime of t. And on the bottom, you need the derivative of x. So that would be x prime of t. And so I'm going to have Mathematica find the derivative, which I am calling my slope function. So it's 1 plus 2t over negative 1 plus 2t. Now that we have our slope function, we want to actually find the slope. So what I'm going to have Mathematica do is I'm going to evaluate my slope function at whatever t value the problem says. Like I said a few minutes ago, we're going to use t equals 1. So I'm going to evaluate m of 1 for my slope value. So it would be 3. So I now have the slope of my tangent line. The next thing I want to have Mathematica do is actually find the equation of the tangent line. So we're going to use a built-in code that I went over in the first video, which is called solve. And so remember, if we click on solve, do the double down arrow and just click the first one. Let me scroll up a little bit so y'all can see. We need to tell Mathematica what formula or what equation we need to solve. So you might remember back in your algebra days, when you found the equation of a line just generally, you would typically start with point slope form and then convert that into slope intercept form. I'm going to do exactly that in Mathematica. So here's how it works. Remember what your point slope formula is from algebra. It is y minus your y value. Now this problem did not give me the y value, so I have to have Mathematica find that. So to find my y value, I'm going to have Mathematica evaluate my y function at 1. Now do keep in mind, this is not me saying it's y sub 1. This is actually y of 1. I want to know what the y value is at t equals 1. Typically, you would do an equal sign, but remember from the first video, if you do an equal sign inside of a built-in code, you have to use a double equal sign. Then we need our slope, which we just found to be 3. And we're going to multiply that. And this is where I'm going to use parentheses for one of the first times. I want to group the next two things together, which is x minus my x value, which once again, I do not know what that is. So I'm going to let Mathematica find my x value at t equals 1 and then close my parentheses. This is my point slope formula. And what you got to tell Mathematica to do now is what letter do you want to get by itself? And as you might remember from algebra in slope intercept form, you want to get the y by itself for it to be in slope intercept form. So let's let Mathematica run this. And as you can see, it's going to give you a little bit different form than you're used to. That's fine, just go with it. This says that the equation of the tangent line is y equals 3 times 1 plus x, which is the same thing as 3 plus 3x. So we have our tangent line. I now need Mathematica to actually put this tangent line on that graph that I did above. Here I think is the easiest way to do it. Step number 1, we're actually going to go back to a previous line of code and add something, and you'll see why in a few minutes. If you go back up to my parametric plot or your parametric plot if you're following along, since I have to combine this with something else in just a minute, I'm going to call this some variable. Typically, I'm going to call this P1. Now, you'll notice that my graph grayed out because it sees that you're trying to edit the code. I'm going to go to the very end and re-input this. You'll notice nothing changes because I didn't change the actual code. I just changed what it's being called. It's being called P1. Now, if I scroll back down, I want to now do a P2 graph. But a tangent line is not a parametric graph. It's a regular Cartesian graph. So I'm going to go back in order to find a regular plot. We did this back on the very first video, and I'm going to plot, double down arrow, the first one. I'm going to plot the equation of the tangent line it just gave me, which is 3 times 1 plus x. Now, obviously, the variable now is back to x. There's no t here. And I need to have an x min and an x max. What I would honestly do is look back up at your picture from above, because you're about to put these together. And since my parametric graph looks like it starts a little bit left of 0 and goes all the way out to 12, I'm going to use that as my guide. Let's go from, let's say, -1, and we'll just go out to 12 because it's there. And then we'll click on the end, and I'm going to plot my graph. Now, obviously, these two graphs are separate, and I want to put them together. Here's why I called one graph P1 and one graph P2. Since both of these were graphed using different built-in codes, the only way that you can put them together is in Mathematica, we're going to use what's called a show function. Now, for the show function, all you're going to do is type in show with a capital S and then open bracket, and you're going to tell Mathematica which two graphs you want to put together. Well, I called them P1 and P2. I want to have Mathematica put P1 and P2 together. And so if I do that, you'll notice that it puts both of those graphs exactly together on my same plot. And you can easily verify that this does look like a tangent line, and therefore I have found a correct tangent line by using my techniques learned from lecture and verified by putting them on the same plot. Very good. And so that's a very simple way in order to do a tangent line problem if I have you do that on your project. All right, we're going to do a couple of other applications here. Before I do that, remember that when you start a new type of problem, you want to make sure you clear any variables that you've already used. So we're going to use clear. And what variables have we used? We defined what x was, y, m, p1, and p2. And so remember, they're all black text because Mathematica knows what they are. When I input these, they all turn blue. And so now I'm ready to start a brand new problem. And so what I'm going to do now is I'm going to work on a length of a curve problem. And this is something, once again, we covered during lecture. And so now I'm going to show you how to do it in Mathematica. So length of a curve requires you to know a parametric equation and an interval, and there's a formula we went over in class of how to do this. So let me give you an example of a parametric equation. So we're going to use a new x of t and a new y of t. So make sure you use your underscores again. For x of t, we're going to do an e raised to the t, so exponential of t, minus t. So let me input that. And then for y of t, we are going to use 4 times the exponential or e raised to the t over 2, and input that. And so I want Mathematica to find the length of a curve between 0 and 2. So if you go back into your lecture notes, you will see that the formula to find the length of a parametric curve is going to be the definite integral from your two values. And like I said, we're going to go from 0 to 2. Within your integral, you have to apply a square root. And inside of the square root, you want to square the derivative of x and the derivative of y and add those together. So in Mathematica, we'll type it in this way. We're going to do x prime of t raised to the second because I want to square it. And then we're going to add to that, open parentheses, y prime of t and square that. And I want Mathematica to integrate this with respect to t. That is our length of a curve formula. And so we're going to apply this directly to see what it is. So let's input this. And there you go. It has an exact answer of 1 plus e squared. Now, always remember, Mathematica will give you an exact answer if that's what it can do. If you want a decimal answer, remember the very next line of code needs to be n of percent, and then we can find a decimal approximation of about 8.38906. And that's all you have to do to find the length of a curve parametrically. Now, After we did length of a curve during class, we then talked about surface area. So we want to make sure we can do a surface area problem in order for this to work. So before I define a new function, let's clear what we did. So this time I only have used X and Y since the last clear. So you see those are black text. Let's clear those. And let's define one more combination of X and Y. So we're going to do X of t. This time, let's let it equal 2t squared plus 1 divided by t. Then we're going to do y of t is equal to 8, and I'm going to use a shortcut here, times the square root of t. So I have my two functions. And so what I want Mathematica to do is to find the surface area of this rotated around. And we're actually going to do both axes here just to show you that it doesn't matter. So let's first do around the x-axis. So if you go back into your notes from class to find the surface area of an object around the x-axis, we're going to begin with the constant that we factor out front, which is 2 pi, times the definite integral. All right, and then so we're going to go from 1 to 3. Hopefully these numbers I picked work out. And since we're going around the x-axis, the function that goes in the front is actually the opposite, which is y of t. Remember, that comes from the idea of cylindrical shells from Cal 2. We are then going to multiply this by the length of a curve, which we just went over. So I'm going to do square root of x prime of t squared plus y prime of t squared. And I want to integrate all of this with respect to t. And so that is my formula to find the surface area of this equation going around the x-axis. So let's see if I picked good enough numbers for Mathematica to do. All right, and so there you go. It's a pretty ugly answer. It's 32 over 15 times 3 plus 103 root 3 times pi. That is never a problem I would make you do by hand in a test, but Mathematica was able to spit it out in a couple of seconds. Now I'm curious about what that is, so let's do capital N. So it's about 1,215 squared units. Now keep in mind, you can also go around the other axis. Now I'm gonna be a little lazy here, and you can do this as well if I ask for both. Now that I've coded one, I'm going to copy the previous code, and nicely you can actually copy and paste codes within Mathematica. Now, the last one I went around the x-axis. This time I want to go around the y-axis. Now the good news in parametric, the only difference is the function that you would put in the front. Because if you're going to go around the y-axis, you need to have an x of t in the front. So I'm going to change that y of t to x of t, and other than that, everything else should be the same. So let's input that. And you see it actually comes out to be, I would consider, a little bit nicer number. 3,104 pi all divided by 9, which decimally is approximately 1,083.5. And so it's simply just applying the formula that you learned during class, but using more complicated functions because you're going to have Mathematica do all the work for you. And so within this video, we covered the basics of how to do parametric information. So how do you define a parametric equation in 2 dimensions? We talked about how to plot one. We talked about how to find the equation of a tangent line. We talked about how to find the length of a parametric curve. And we finally ended talking about surface area. And so that should give you a great foundation in order to help you work on your project that you have in my class. That puts a wrap on video number 3. In the next video, we're going to move to the next idea that we covered in class, which was polar equations. And so when you come back, I'll talk about how polar works within Mathematica, and we'll do a few examples as well.